This is part of 14D in the textbook. When do we use the double angle formulas? So there are plenty of formulas and they're listed in this table below. So we use these when we don't know the value of sine, cos, or tan of a particular angle given, but we do know the value of the sine, cos, or tan if the angle was halved. Let's have a look at an example. I want you to imagine that I asked you to find the value of sine pi on 3 radians, also known as sine 60 degrees, and you completely forgot what sine of 60 degrees, but for some reason you know what sine of 30 is. So notice that sine of 60 or sine pi of 3, I can really write that as sine of 2 times 30 degrees or 2 times pi on 60. Now using that first formula I have that says sine of 2 times some angle is equal to 2 times sine of that angle times cos of that angle. So I could rewrite this as 2 times sine pi of 6 times cos pi on 6. Now, like we said, you know what sine pi of 6 is, and you know what cos pi of 6 is. So we have the 2 still. Sine pi of 6 is a half, times it by cos pi of 6, which is root 3 on 2, and I'll end up with root 3 on 2. So sine 60 is root 3 on 2. Let's prove the double angle formula for cos 2 theta. So I'm trying to prove that cos 2 theta is equal to cos squared theta minus sine squared theta. We're going to use some addition rules that we learned previously to help prove this. Recall that cos 2 theta, I could rewrite this as cos theta plus theta, right? That will give me 2 theta. And now I can use the addition formula. So remember that cos likes to stay together. So the addition formula will be cos times our first angle in the brackets, which was theta, times again cos, this time the second angle in our brackets, which was theta. We'd make it a minus sign, the opposite sign that was in our brackets, and we now take sine. So sine of the first angle theta times sine of the second angle theta. Cos theta times cos theta is cos squared theta. Sine theta times sine theta is sine squared theta. And notice I've just proven the formula that cos 2 theta equals cos squared theta minus sine squared theta. But that's not the only way it could be presented. We also have that cos 2 theta equals 2 cos squared minus 1. Let's prove that using what we've got so far. So notice that sine squared theta plus cos squared theta equals 1, or sine squared theta equals 1 minus cos squared theta. I'm going to sub this value of sine squared theta into my equation start, and I'll keep the cos squared theta minus, well, sine squared theta is 1 minus cos squared theta from my Pythagorean identities. And then I'm just going to expand those minuses out. So I'll get cos squared theta minus 1 plus cos squared theta. That equals 2 cos squared theta minus 1. All right, so now I've proved the second version of the formula. There's one more version. Again, using sine squared theta plus cos squared theta equals 1. I know that if I rearrange that, cos squared theta equals 1 minus sine squared theta. So let's sub this into that second version of the formula that we proved. If I have 2 cos squared theta minus 1, I'm going to sub in 1 minus sine squared theta everywhere I see a cos squared theta, and I'll get 2 times 1 minus sine squared theta minus 1. Expanding and simplify it, I'll get 2 minus 2 sine squared theta minus 1. 2 minus 1 is just 1, so I'll get left with 1 minus the 2 sine squared theta. Example 2. This time we're going to use tan. It says if tan theta is 4 on 3, and we know our theta is acute, right? It's between 0 and 90 degrees, or 0 and pi on 2 radians, find sine 2 theta. To find sine 2 theta, I need to find sine theta and cos theta. And I can figure this out using my right angle triangles. So if tan theta is 4 and 3, my opposite is 4, my adjacent is 3. That makes my hypotenuse, using Pythagoras, 5. So now I can figure out what sine theta is and cos theta is. Sine 2 theta equals 2 times sine theta times cos theta by the formula. Sine theta is opposite over hypotenuse, so 4 over 5, and cos theta equals adjacent over hypotenuse, or 3/5. Subbing this in, I'll get sine 2 theta is equal to 2 times sine theta 4 and 5 times cos theta, which was 3/5. Putting this all together, 2 times 4 times 3, that's 24. 5 times 5 is 5. And because the angle is in the first quadrant, both sine and cos are positive. So that is all good. Part B, I need to find tan 2 theta. This one's nice because I can just use the formula, the third one down the bottom. So tan 2 theta is equal to 2 tan theta divided by 1 minus tan squared theta. Now it told me already what tan theta is, so this is just a matter of substitution. Tan theta is 4 over 3, so everywhere I see a tan theta, I'm going to put 4/3. Remember on the base, it's 1 minus tan squared theta, so square your 4/3. And again, if we simplify this, we get minus 24 over 7. And it's okay that this is a negative, because remember, if theta alone was acute, then 2 theta could actually be obtuse, and tan is negative for obtuse angles. Last question, we're going to try and prove this statement. So to prove something, we've got to show the left-hand side is equal to the right-hand side. First step, I'm going to take the left-hand side, manipulate it so it looks like the right-hand side, but only touching the left-hand side. So first I want to do is I want to cross multiply the left-hand side, make a common denominator. So the first fraction, I'm going to multiply the bottom and the top by cos theta minus sine theta. 1 times cos theta minus sine theta is just cos theta minus sine theta on the numerator. And then my denominator, I'm just going to multiply it, but leave the brackets. The second fraction, I'm multiplying by cos theta plus sine theta. So that's easy for the numerator because I've just times it by 1. And then what we're going to do is put it all together in one common fraction. So I'll get cos theta minus sine theta plus cos theta plus sine theta all over cos theta plus sine theta times by cos theta minus sine theta. Expand and simplify. So simplify the top, collecting your like terms, and then expand the bottom and simplify it. And notice we have something nice on the bottom and the top. So on the top, I have cos theta plus cos theta, so that's 2 cos thetas, minus sine theta plus sine theta. The sine thetas will cancel out, so I'm just left with 2 cos theta on the numerator. And on the denominator, I'm going to be left with, well, this is nice. I'll have cos squared theta. Then I'll have minus sine theta cos theta plus sine theta cos theta. So those two will cancel out. And then lastly, I'll have minus sine squared theta. Okay, this doesn't look anything like tan and cosec. But let's maybe simplify a little bit more. Notice using our double angle formulas that cos squared theta minus sine squared theta, well, that could be written as cos 2 theta. I'm going to put this in and see where it gets us. Now, on the right-hand side of my formula, I have a tan 2 theta. I know something about tan 2 theta. Tan is usually sine over cos. We're going to use that to help our left-hand side look like the right-hand side. We need tan 2 theta, so I know that will be sine 2 theta over cos 2 theta. I also already have a cos 2 theta on my left-hand side, but I want a sine 2 theta on the numerator. So if I can make my numerator look like sine 2 theta, or look like 2 sine theta cos theta from my double angle formula, I can end up with a tan 2 theta. So let's use part 1 of our double angle formula. I'm going to multiply both the numerator and the denominator by sine theta to get the top to be something that is sine 2 theta. So on the top I'll get 2 cos theta sine theta. On the bottom I'll have cos 2 theta, but remember I'm multiplying it by sine theta. So on the top I'll get sine 2 theta, and on the bottom, well, the cos 2 theta will still be there, and I'll still have the sine theta there. And here we go, the best part, we have a tan, sine 2 theta over cos 2 theta. That's going to give me my tan 2 theta. And remember that 1 over sine theta is really cosec theta. So that's how that fits in. Now, indeed, if I sub 1 over sine theta to be cosec theta, I get tan theta times cosec theta. And in that way, my left-hand side equals my right-hand side, and I have proven this statement. Mathematicians aren't people who find maths easy. They're people who enjoy how hard it is.